Okay, so I wanted to make a short video about real applications of complex numbers, which sounds a bit stupid. Why would something imaginary have real application? And you'd be surprised, there's a lot of real things you can do with complex numbers. And here is one of them, is evaluating trigonometric functions. So let's start off simple with the modulus argument form of a complex number. I'm assuming you'll know what an Argand diagram is and the way to show a complex number on there. So if we have a small diagram here, can you see that? Okay, and a complex number here, and the modulus of the complex number to the point there, if we take cosine of the modulus there, that would be this horizontal line, and then sine of that modulus would be that vertical line. So using this is the real and the y is the imaginary, you can write the complex number as the modulus times cosine of the argument plus I sine of the argument as well. So that's a modulus argument form of a complex number. And the Euler's formula says that e to the I theta equals cosine theta plus I sine theta. And if you want me to prove that, I can do it in another video, because it's it's not a long proof, but it's a little bit more complicated than this. And well, here we have a fairly simple expression, and say I wanted to isolate cosine on its own. Thinking about that, I could do e to the I theta plus e to the minus I theta. I could do the complex conjugate of this, so that would give me cosine theta plus I sine theta minus, plus cosine theta minus I sine theta. The reason this is the way that it is because cosine of a minus angle is just the angle without the minus, because cosine is an even function and sine of a minus angle is minus sine of the angle because it's an odd function. If I then expand all that, I get 2 cos theta just on its own, because those two cancel. And so if I then divide all of that by 2, I get the cos function. So cos can be described as that, and sine can also be described as e to the I theta minus e to the minus I theta over 2i. So this is really useful, and I'll come back to that in a moment, but for now I want to do something a little bit more simple. Let's say the compound angle formula. So given the complex number e to the I a plus b is then equal to, using the rule of powers, e to the I a times e to the I b, which would then be equal to cos a plus I sine a times cos b plus I sine b. Expanding that out, we get, I'm going to need more room for this, this will be long, cos a cos b plus I sine b cos a plus I sine a cos b minus sine a sine b, right? And then for the real part of this, which is the cosine, my pen's running out, equals cos a plus b. If we get rid of all the imaginary things there, it becomes, wait, I times I, actually that becomes plus. What am I talking about? That's plus. Yeah, that's plus. That's not plus, that's minus. Yeah, minus. What am I talking about? Minus. Idiot. Stupid boy. That means that cos a cos b minus sine a sine b is the compound angle formula for cosine, and for sine it would be the imaginary part of the complex number, which is sine b cosine a plus sine a cosine b, which is the compound angle formula for sine A plus B. And then for the minus versions, you just flip the signs around there. And going back to what I wanted to say before about this, you can use this to find things as well. For example, the cubic reduction formula for sine, if I have sine cubed theta, we know that sine cubed theta equals 3 sine, oops, I wrote that wrong, 3 sine theta minus sine 3 theta over 4. But what if I want to prove that? You might get asked that in an exam, how to prove this identity, and you can use it. You can do it using other identities, but I really like this way of doing it. Using this, well, I'd be using the sine one. So that would become e to the I theta minus e to the minus I theta, all cubed, because it's sine cubed, over 2, or actually the 2 becomes cubed, so 8I cubed. And then expanding that, we would get minus 1 over 8I. Using binomial expansion, you can do e to the I theta cubed minus e to the I theta squared, or 3 e to I theta squared, e to the minus I theta minus 3 e to the, minus 3 e to the I theta e to the minus I theta squared, and then minus e to the minus I theta cubed, and then expanding all that out and putting it into the form of this before, we get it. Can you even see it? Yeah, you can see it. Taking everything out to get it into the form of this, like I said before, but it would be sine, so it would be e to the I theta minus e to the minus I theta over 2I. I can expand to get 3/4 e to the I theta minus e to the minus I theta over 2I minus 1/4 e to the I 3 theta, because using the power of indices, that I theta cubed becomes I 3 theta minus e to the minus I 3 theta over 2I. And then we're putting that into the form of this is sine and this is sine 3 theta all over 4, so that becomes 3 sine theta minus sine 3 theta all over 4. And there you have proved the cubic reduction formula for sine. So complex numbers have a really good application to real life. Yeah, I mean, I find this personally a lot easier to prove than using standard trigonometry, and in an A-level exam I would do exactly the same here. And I'm sure you'd get the same marks for it because it's not wrong at all, it's perfectly right, perfectly legitimate. Yeah, and for example, there's many other examples too, like for example the double angle formula. I can do that at the bottom here, because that's really simple. Cosine of 2 theta plus I sine 2 theta equals cos theta plus I sine theta all squared, which equals cos squared theta plus 2I sine theta cos theta plus sine I sine I squared sine squared theta. And then for the real part, which is cosine, can you see this at all? I don't know if you can see this. Equals cos 2 theta equals the real part, which is just cos squared theta plus or it'd be minus, because I squared is minus 1, minus sine squared theta. Yeah, my hair is so fucked, what's going on? And then the imaginary would just be the sine part, equals sine 2 theta equals just 2 sine theta cos theta. And I've just proved both of the double angle formulas for cos and sine using de Moivre's theorem. So this is a really, really important skill to have, and it will really benefit you in A-level maths, I think. I mean, you get taught this in further maths, I know for sure, but this will really help you in normal A-level maths. So thank you for watching.